All right, let's jump right into this explainer. Today, we're diving headfirst into the wildly fascinating world of AI memory systems. As AI agents start taking on these massive, complex, real-world tasks, we're going to look closely at exactly how developers are teaching language models to remember things over long periods of time. And honestly, perhaps even more importantly, how they are teaching them to forget. We really got to start with this critical question that literally every developer hits at some point. What happens when we push AI beyond just simple one-off Q&A? When we ask an AI to manage long-term projects or tackle a task that takes dozens of steps, why does it inevitably eventually crash or just start hallucinating? If you've ever tried to have an agent manage a complex coding project, you know exactly what I'm talking about. Eventually, the AI just completely loses the plot. Well, the villain in this story is something called context window explosion. Think of it like this. Every single time an AI uses a tool or runs a web search, it dumps all that raw data, which is often thousands of tokens, straight into its active working memory. When this passive junk just keeps accumulating, it causes what's known as context rot. So after maybe 100,000 tokens or so, an AI that was brilliant 5 minutes ago suddenly becomes incredibly slow, super repetitive, and just deeply confused. So here is our roadmap for today's explainer. We'll start with the core AI memory problem, look at choosing your memory system, introduce the ReMe framework, solve that context explosion issue, dive into the art of forgetting, and finally, look at how smaller models can actually have bigger brains. Okay, section 1, the AI memory problem. Here's the thing, traditional AI fundamentally relies on a passive accumulation paradigm, meaning it just keeps appending every single conversation, every tool result, every minor error into this one static archive. It's literally like throwing every single piece of mail, junk or otherwise, into a giant pile on your desk. Eventually, you can't find the bills you need to pay. Actually, it's more like you just run out of physical space to put anything new down at all. The AI simply runs out of cognitive space to process anything new. Moving right along to section 2, choosing your memory system. Right now, the whole ecosystem of memory tools is, frankly, completely fragmented. There really isn't a single best system right now. The right choice depends entirely on your specific use case. For example, if you just want to remember user profiles for a basic AI companion, Memobase is going to be your go-to. But if you're trying to manage complex, shifting relationships and preferences over time, you'd want to look at Zep's timeline and graph database approach. Or, hey, if you're doing heavy multi-document reasoning, Cogni's method of turning RAG into a knowledge network is absolutely ideal. To kind of wrap your head around the architectural differences out there, let's contrast two totally opposite approaches, Mem0 and Letta. Mem0 takes a really lightweight, plug-and-play middleware approach. It just sits nicely outside your app. Letta, on the other hand, which you might remember as MemGPT, acts much more like a heavy, built-in operating system. You literally have to build your entire agent inside Letta's world so it can deeply control its own memory state. Which brings us to section 3. Let's introduce the ReMe framework. This is where things get super interesting. If you have an agent without procedural memory trying to execute a stock trade, say buying Apple stock at the prevailing market price, it's highly likely to just hallucinate a fabricated price out of thin air. But a ReMe-equipped agent pulls from past experience. It knows that to get that prevailing price, it first needs to actually use a tool to pull real-time data before safely placing the order. It actually learned a procedural rule. So how does ReMe pull this off? Well, it mimics human cognition through this dynamic 3-phase lifecycle. First up is acquisition. Here, it extracts fine-grained lessons from both its successes and failures, figuring out exactly what went wrong or right in a given task. Second is reuse. And this is key. It doesn't just copy-paste past answers. It dynamically rewrites historical insights to fit the nuances of a brand new context. And third is refinement. It continuously optimizes its own memory pool. It autonomously adds new valid memories as it learns, while aggressively pruning and throwing away outdated or bad ones so they don't corrupt future tasks. All right, section 4. Let's talk about solving that dreaded context window explosion. Without managing context, traditional agents just hit a total brick wall after maybe 15 or 20 complex tool calls. They literally exhaust their tokens and just fail. But ReMe uses this thing called a message offload. It acts exactly like a human filing cabinet, intelligently moving non-essential, bulky information completely out of the active context. This theoretically allows the agent to operate infinitely without losing its mind. To pull this off, the system relies on three really smart strategies. First, there's message compaction. This takes massive data blocks, like, say, the raw HTML of a web search, and stores them in external files, leaving just a tiny file path in the active memory. Second is message compression, where the LLM actually generates a concise summary of older conversations. And finally, the third strategy is a hybrid auto mode. It acts like an intelligent traffic controller, dynamically switching between compaction and compression to maintain this perfect Goldilocks zone of about 10 to 30,000 active tokens. Now, you might be wondering, so what? Well, by leveraging these offloading techniques, long conversations see an absolutely massive 70 to 90% reduction in token consumption. 70 to 90%. That doesn't just save the AI's brain, it drastically optimizes your API costs. On to section 5, the art of forgetting. This is honestly the most human aspect of this whole framework. Just like you and me, an AI actually needs to forget useless trivia so it can remember the stuff that actually matters. As the researchers point out, retaining outdated or harmful experiences actually degrades performance over time. Think about it. If a website's API changes, the AI's old memory of how to use it instantly becomes toxic noise. It has to be able to let it go. And you can see the real-world impact of filtering out that noise straight in the data. When ReMe is applied, reasoning errors drop substantially, from 22 down to 14, and action omissions drop right along with them. This is hard proof that by actively pruning bad memories, ReMe completely stops the propagation of those multi-step mistakes that usually derail long-horizon tasks. Finally, Section 6, Smaller Models, Bigger Brains. This benchmark data is genuinely the real wow factor of this explainer. When put to the test on complex tasks, a smaller 8 billion parameter model, but one equipped with ReMe's dynamic memory, actually outperformed a much larger 14 billion parameter model that lacked memory. The 8 billion model hit a 55.03% success rate, barely edging out the larger model's 54.65%. This is revolutionary. It proves you can save massive amounts of compute power and money just by giving a smaller AI a better memory system. We even see this holding true in spatial and physical navigation tests. Take the slippery frozen lake experiment, which is a classic reinforcement learning benchmark where an agent has to navigate a really hazardous grid. Adding task memory directly boosted the QN3-8B agent's survival and success rate from 66% up to 72%. It learned the layout, remembered the safe paths, and perfectly applied that knowledge. And that essentially wraps up our explainer. But before we go, I want to leave you with this kind of mind-bending thought to chew on. If procedural memory provides a computation-efficient path for self-evolving AI, if a smaller model can seriously outsmart a massive one simply by remembering, reflecting, and refining its experiences, what entirely new capabilities will lifelong learning unlock next? As agents stop just reacting and start truly accumulating wisdom, the entire landscape of artificial intelligence is going to change forever. Thanks so much for joining me on this deep dive.